Welcome back to the Deep Dive. I'm your guide, and today we're diving into something really central to chemistry, chemical reactions. We often picture them as, a one-way street. Reactants go in, products come out, done. But what if I told you that actually a lot of reactions are more like a constant dance?
That's a great way to put it. Not a one-way street, but maybe like a busy bridge. Cars going both ways. And even though individual cars are always moving, the number of cars on each side stays, well, pretty much the same. It finds a balance.
A dynamic balance. And that is exactly what we're talking about today, chemical equilibrium.
Hmm.
We're going to build on some things you might already know from, say, thermodynamics, heat, spontaneity, and also kinetics, reaction speeds. Our mission today,
Yeah.
to really get under the hood of this equilibrium idea, figure out how reactions find this balance, and how we can even predict or change it.
Yeah, we'll look at what equilibrium actually is, and then we'll introduce a really key number, the equilibrium constant. We call it K. K is basically like a blueprint. It tells you exactly where that balance point lies for a specific reaction at a certain temperature. It's powerful stuff.
And once we've got K sorted, we can use something called the reaction quotient,
Yeah.
Q, to see which way your reaction is heading before it gets there. We'll also look at Le Chatelier's principle. Sounds fancy, but it's a great way to predict how systems react when you, well, mess with them. And finally, we'll touch on how chemists actually calculate things using something called ICE tables. Okay, so let's start simple. Reversible reactions. Sometimes you see equations with this one arrow, right? Reactants and products.
Those are the ones we often think go pretty much to completion, like burning carbon completely to get carbon dioxide. C plus O2 gives CO2, mostly a one-way trip.
But then you see that other symbol, the double arrow. That signals it's reversible.
Exactly. Reversible means it can go forwards and backwards. Think about ammonium chloride, NH4Cl solid. It can break down into ammonia gas, NH3, and hydrogen chloride gas, HCl. But those two gases, they can react right back together to form the solid again.
And here's the important bit. Many, maybe even most, real-world chemical reactions have this reversible nature, which leads us straight to equilibrium.
Right. So chemical equilibrium, in simple terms, is that state of balance. It's when the speed, the rate of the forward reaction exactly equals the rate of the reverse reaction. And the crucial outcome of that is the amounts, the concentrations of your products and reactants. They stop changing. They stay constant.
Okay, wait, so the reactions don't actually stop? It's not like everything just freezes?
No, absolutely not. That's key. That's why we call it dynamic equilibrium. Dynamic meaning active, moving. The forward and reverse reactions are still happening constantly. Molecules are changing back and forth. But because the rates are equal, there's no overall change in how much reactant or product you have. It just looks stable from the outside.
Ah, okay, dynamic. Got it. So what are the hallmarks of this state? How do we know we're there?
Well, typically you need a closed system. You can't have stuff escaping or coming in, usually. And importantly, both reactants and products are present. You haven't run out of anything. And like we said, the forward and reverse rates are perfectly matched.
And I read something fascinating. You can actually reach this equilibrium point no matter where you start.
That's right. You could start with only reactants or only products or some mix. Let them react in a closed container at a constant temperature, and eventually they will all settle at the same relative amounts, the same equilibrium position. And once you're there, concentrations, pressure, temperature, even visible things like color, they all stay constant.
What about catalysts? They speed things up.
Right.
Do they change the equilibrium?
Good question. A catalyst speeds up both the forward reaction and the reverse reaction, and it speeds them up by the same amount. So the net effect, it helps you get to equilibrium much faster, but it doesn't change where the equilibrium lies. It doesn't change the final balance point or give you more product in the end if the equilibrium naturally doesn't favor it.
Okay, that makes sense. So equilibrium is the state, but you also mentioned the equilibrium position. What's that about?
Right. The position just tells us about the relative amounts. Once you're at equilibrium, do you have mostly reactants hanging around or mostly products? If we say the equilibrium lies to the left, that means reactants are favored. You've got a higher concentration of reactants than products. Maybe the reaction isn't very efficient under those conditions.
Yeah, if it lies to the right.
Then products are favored, higher concentration of products compared to reactants. This suggests the forward reaction is more successful, more productive under those conditions. It tells you which side of the equation sort of wins when everything settles down.
So how do we put a good number on this?
Yeah.
How do we quantify where that balance actually is?
That brings us to the big one, the equilibrium constant, K. This idea goes back to Goldberg and Wage, two Norwegian chemists, way back in 1864. They came up with the law of mass action.
Okay, law of mass action. How does it work for K?
So for a general reaction, let's write it as, say, lowercase a moles of reactant A plus B moles of B are in equilibrium with C moles of product C plus D moles of D. The expression for K is basically products over reactants raised to the power of their coefficients from the balanced equation. So K equals C to the power C times D to the power D, all divided by A's to the power A times B to the power B.
And those square brackets, D, mean concentration, right? Usually molarity, moles per liter.
Exactly, molarity at equilibrium. And here's the really, really crucial part. For a given reaction at a specific temperature, K is a constant. It doesn't change. That number K tells you the inherent tendency of that reaction to reach a certain product-to-reactant ratio at that temperature. It's like a target value.
And what does the size of K tell us?
That's where it gets practical. If K is really small, like much less than 1, it means the denominator, reactants, must be much bigger than the numerator, products. So K1 means equilibrium lies way to the left. You mostly have reactants.
And if K is huge, much bigger than 1,
then the numerator products must be much larger. K1 means equilibrium lies far to the right. You mostly have products. The reaction strongly favors product formation.
It's like a score for how much product you get. Got it. Are there rules if we manipulate the reaction equation, like flip it around?
Yep, very logical rules based on the math. If you reverse a reaction, the new equilibrium constant, let's call it K, is just 1 divided by the original K equals 1K.
Makes sense. If it favors products one way, it must favor reactants the other way.
Exactly. And if you multiply the whole reaction equation by some factor and like doubling all the coefficients, the new K is the original K raised to the power of n.
Okay, and combining reactions, adding them together.
If you add two reactions to get a net reaction, the K for the overall reaction is the product of the individual K values. Net equals K1, K2.
These rules seem really useful for linking different reactions together.
They are, especially when you're dealing with multiple steps. Now, for gases, we sometimes use pressures instead of concentrations.
Right, you mentioned Kp. Kc uses concentration, Kp uses partial pressures.
That's it. The expression looks the same, but uses partial pressures P instead of concentrations. Kp is PCC, PDD, PAA, PVB.
Is there a link between Kp and Kb?
There is. Kp PAA times RT raised to the power of Dungas. R is the ideal gas constant. T is temperature in Kelvin and Dungas. That's the change in the number of moles of gas between products and reactants. So total moles of gas products minus total moles of gas reactants.
So Kp only equals Kc if the number of gas moles doesn't change in the reaction, when Cungus is 0.
Yeah, precisely. If Angus is 0, that RT0 term becomes 1 and Kp equals Kc. Otherwise, they'll be different.
Okay, one more really important point about writing these K expressions. What about solids and liquids?
Yes. Pure solids and pure liquids are not included in the K expression, whether it's Kc or Kp.
Why is that?
Because their concentration, or their effective concentration or pressure, doesn't really change during the reaction. Think about a solid. Its density is constant. Its concentration in itself is constant.
K tells us the destination, the equilibrium state. But what if we're not there yet? How do we know which way the reaction needs to go?
That's where the reaction quotient, Q, comes in. It's our navigator. Yeah. Q has the exact same mathematical form as K products over reactants raised to their powers. But the crucial difference is Q uses the concentrations or pressures that you have right now at any given moment, not necessarily at equilibrium.
So K is the target value. Q is where we are now. How does comparing them help?
It tells you everything. If your calculated Q is less than the known K value, QK, it means your current ratio of products to reactants is too low. You don't have enough products yet. So the reaction needs to shift to the right, make more products to reach equilibrium.
Okay, and if Q is greater than K?
If your ratio of products to reactants is too high, you've kind of overshot the equilibrium mark or started with too much product, the reaction needs to shift to the left, convert some products back into reactants to reach equilibrium.
And if, by chance, Q equals K?
Then you're already there. The system is at equilibrium, no net change will happen. So calculating Q and comparing it to K is like checking your reaction's GPS. Am I there yet? Do I need to go forward or backward?
That's a really clear way to think about it. Okay, so Q tells us how to get to equilibrium. But what if we are at equilibrium, and then we deliberately disturb it? Add something, change the temperature.
Now you're talking about Le Chatelier's principle. It's a fantastic qualitative guide for exactly this. Basically, it says, If you impose a change, a stress, on a system at equilibrium, the system will shift in a way that tends to counteract or minimize the effect of that change. It's like
Yeah.
the system pushes back to try and restore balance, or at least find a new balance that absorbs the disturbance.
Nature fighting back,
Yeah.
sort of. So how does it work with specific changes? Let's start with concentration.
Okay, if you're at equilibrium and you add more of a reactant, the system says, whoa, too much reactant, and shifts to the right to use up some of that added reactant and make more product. Conversely, if you add more product, it shifts left to use up the extra product. Same idea, if you remove something, removing product pulls it right, removing reactant pulls it left.
And does K change when we do this?
No. Critically, K stays the same. The system just adjusts the concentrations to get back to that same K ratio.
Okay, what about pressure or volume, especially for gases?
This matters mainly when the number of moles of gas is different on the two sides of the equation. Angus, Ado. If you increase the external pressure, maybe by squishing the container volume down, the system feels squeezed. It will shift in the direction that produces fewer moles of gas because fewer gas molecules take up less space and exert less pressure.
And if you decrease the pressure, like expanding the volume.
It shifts the other way towards the side with more moles of gas to try and fill that extra space and increase the pressure back up. And again, K itself doesn't change with pressure or volume changes.
Right, now the big one, temperature. You said this does change K.
Yes, temperature is the only thing that changes the actual value of the equilibrium constant, K. Think of heat as a reactant or product. For an endothermic reaction, one that absorbs heat and K is positive, heat is like a reactant. So if you increase the temperature, add heat, you're adding a reactant. So the equilibrium shifts to the right towards products to use up that extra heat and K increases.
And for an exothermic reaction, releases heat, AH negative. Heat is like a product.
Exactly. So if you increase the temperature, you're adding a product. The equilibrium shifts to the left towards reactants to use up that heat, and K decreases. Lowering the temperature does the opposite. In each case favors the exothermic direction.
So changing temperature not only shifts the position, but changes the fundamental balance point, K. That's a key difference. And just to be absolutely clear, adding a catalyst.
Still no change to equilibrium. As we said, it speeds up both forward and reverse reactions equally, gets you there faster, but doesn't change the destination at K or the final balance position.
Perfect. Okay, we understand the concepts, K, Q, Le Chatelier. But how do we actually calculate concentrations? You mentioned ITE tables.
Yes, the ICE table is a super common and really useful tool for organizing equilibrium calculations. ICE stands for Initial Change Equilibrium.
How does it work?
You basically set up a table under your balanced chemical equation. The I row is for the initial concentrations or pressures of everything before the reaction starts shifting towards equilibrium. The C row represents the change in concentration as the reaction proceeds. You usually define this change using a variable, like x, and relate the changes for different species using the stoichiometry, the coefficients, from the balanced equation. Reactants decrease, products increase, plus x. And the E row is the equilibrium concentration, which is just the initial plus the change I plus C.
Okay, so you end up with expressions for the equilibrium concentrations, probably involving X.
Exactly. Then you take those equilibrium expressions from the E row and plug them into the equilibrium constant expression, K. Since you usually know the value of K, you now have an equation with X as the only unknown. You solve for X.
And once you have X, you can plug it back into the E row expressions to find the actual numerical concentrations at equilibrium.
That's the process. It can sometimes lead to quadratic equations or approximations depending on the value of K, but the ICE table provides the structure. It's useful for finding K if you know one equilibrium concentration, or finding all equilibrium concentrations if you know K and the initial amounts. You can even use a modified version if you disturb an existing equilibrium. The initial row becomes the old equilibrium state plus the disturbance.
That sounds like a really practical tool. Okay, let's wrap this up. We've covered a lot of ground on chemical
You
equilibrium.
really have, and it's so foundational. Understanding K, this equilibrium constant, is absolutely essential for things coming up next, especially acids and bases. Their strengths are described by dissociation constants, which are just specific types of equilibrium constants. So this K concept is the bedrock.
Definitely feels like a cornerstone concept. So, key takeaways. Equilibrium is dynamic, rates are equal, concentrations constant. K tells us where the balance lies, left for small k, right for large k. Q tells us how to get there. Le Chatelier's principle helps predict shifts due to changes in concentration, pressure, volume, or temperature. And temperature is the only thing that changes K itself. Catalysts just speed things up.
And the ICE table is our friend for doing the math.
Exactly. So here's a final thought to leave you with, stepping back from the chemistry lab for a moment. This whole idea of dynamic equilibrium, achieving stability, not through stillness, but through constant, balanced, opposing processes. Where else do we see this? Think about ecosystems, maybe economic markets, maybe even our own bodies, maintaining temperature or blood sugar, that homeostasis. What can understanding chemical equilibrium teach us about how complex systems, way beyond molecules, find stability and manage change? It's quite profound when you think about it.
It really is. That balance through constant activity, not stagnation, seems to be a pretty fundamental principle across nature.
Absolutely fascinating stuff. Well, that's all the time we have for this deep dive. We hope you feel a bit more tuned in to the elegant dance of chemical equilibrium.